Hi all, welcome to this lecture on channel capacity. The channel capacity result is one of the most fundamental contributions of information theory to many other disciplines. To understand this, let's consider the following setup. So let's say there are three people. One is Alice, then other one is Bob, and there's someone else is actually who's Charlie. And Alice and Bob, they are actually friends. And in this setup, Alice essentially wants to send some messages to Bob. Okay, so Alice is the sender here, and Bob wants to receive the messages from Alice. Whereas what Charlie is doing here, Charlie is a common enemy to both these guys, and Charlie doesn't want that Alice actually talks to Bob. So therefore, it just try to create some some nuisance and some try to create some disturbance in the environment, so that whenever Alice try to send some messages, the Bob could not listen to it. Okay, so for an instance, let's consider the case where Alice sends the first message, and the message is of cat. Okay, so in return, because of the disturbance which was caused by the Charlie in the environment, Bob essentially received this message as let's say bat. Okay, so let's say that there is error at the first location, first letter, and when trying to listen to this, Bob essentially decodes it to be a bat. Then what essentially has to be done by Alice, so as to bypass this noise created by Charlie. So in order to just bypass this noise, Alice comes up with a scheme, and this time instead of simply sending the message cat, this time it also sends a message cat, and then it adds a new piece of information which is actually meow. Okay, so this time it sends cat meow, okay, instead of cat. And then again, let's suppose that you got the error at the first location, that is the first letter. So then Bob essentially should recover something called a bat meow at its end. But then this bat and meow doesn't make sense, and both this piece of information has to make some sense. It can be decoded by Bob that this message was actually cat meow. Okay, and then from this it can actually extract the information cat. Okay, okay, so what has actually happened here? How was this this communication got facilitated? Okay, so yeah, so note that this out of the setup there are three things that has happened after you have added some information in this cat. So let's begin with I list them one by one. So the first thing is that after adding this redundancy, there's extra information, adding some new information, or you can say redundancy. It actually facilitates the communication and increases the so it facilitates the communication. Okay, second point here is that after adding this redundancy, the length of the message actually got increased, right? So the length of message increased, and in fact it actually increased from 3 letters to 7 letters, right? Because this time you have added new information, so you have 7 letters this time. Also, third point is that the new information that you have added to this original message vector, which was cat, is it arbitrary? No, it is not, right? Because this information has not to be arbitrary. This has to be some related information about the original piece of information. Okay, so that means that this message, the extra message that you have sent, which is meow, is actually redundant information which is somehow correlated with the original message. That is, this message choice, the extra message choice that you have added to this cat is not arbitrary. You can't add anything. It has to make some sense. So you have to carefully design your scheme in such a way that uh, you add something to your original message, and then that facilitates essentially the communication, and Bob essentially receives the right message. Okay, so this meow is actually a correlated information, some kind of correlated information that you add to the original message. Of course, it doesn't add any extra piece of information. Okay, what I essentially mean by that is that this is the original message. Meow is not is not carrying any important information. Okay, that simply means that if let's say someone in mathematics, if someone asks you to solve find x and y such that x plus y is equal to 5, and this is the only information that you get, then all you can say out of this x plus y, the information that you get about x comma y pair satisfying this equation is same as is the same information that you get out of this equation here, 5x plus 5y equals to 25. Okay, so both these pieces of information are same. So similarly here also, the information that was carried by cat and the information carried out by cat meow is essentially the same. It's just that there is something redundant going on. Okay, this extra information is not carrying the original message that we want to transmit. So these are the three things with this channel capacity. So sorry, the three things are with this particular setup. So what is our goal? So the goal here is that you want to the general goal is to you want to bypass this some kind of noise that you receive in the communication system, and so essentially in order to bypass this, you add some piece of extra information. In some sense, you say that you have encoded your message from cat to a longer length, which is known as cat mu here in this particular example. So you have you have encoded your piece of information so that this information can actually be the original message can be retrieved from the received vector that the receiver will get. Okay, so of course this how powerful your encoder, what should be your encoding scheme, it actually depends on obvious thing, which is actually a noise or the extra disturbance which was created by Charlie here, and in normal communication systems it's actually a noise. So as of now, you should think the encoder as simply a black box. Okay, in which this is the model that you have. So in which there is a sender which actually got some messages, sequences of messages, which has to send some messages, let's say small m, and there are actually capital M number of messages that it has to choose from, and from this m number of messages, it actually chooses some small m, let's say from this set, and sender essentially wants to first it will go to this black box which is known as encoder. Okay, what encoder what encoder does, it takes the input as m, and then splits out a sequence of number. We consider it to be an n length sequence this time. So for let's say small value n, the encoded output is x1, x2, and so on till xn. Okay, so you give a message m, and after the encoding operation, let's say you get an output x1, x2, so on to xn. Now the thing is, why this encoding is important? You had seen in the early example, this encoder or this encoding operation essentially facilitates the communication, or it just extra adds up a shield to basically your original message, and so as to bypass the noise that it gets. So this is the like n-length sequences, and it actually gets passed down through this block of noise. Okay, known as channel noise. Channel is simply the environment in which you are sending. So channel noise will precisely mathematically define what exactly do we mean by channel. But as of now, heuristically, you can think it as some kind of channel noise you have. And then out of this channel, so you give input this n length bigger sequence x1, x2, and so on till xn, and at the receiver end, as an output of this channel, you receive something like y1, y2, and so on till by end. Okay. Okay, so note that why I will get only n length messages again. This is because you should think this block as using this channel n number of times. Okay, so you can think it as a parallel implementation. You after the encoded output, all the encoded outputs which are of n length. So transmit each of one of them using single channel use. X1 is transmitted in the first channel use, X2 in the second channel use, and you can do all these things concurrently in parallel. And out of this, after this n number of channel use, I'll write it here. So this is after n channel uses. Okay. So after n number of channel uses, the output that you get is sequential again, and this is denoted by y1, y2, and so on till y1. Note that I intentionally put a capital letter here for yi's and small letters for x1, x2, and so on. Because this x1, x2, we have fixed the meshes, okay? We have fixed the meshes m, and accordingly we have a fixed encoded output, which is x1, x2, and so on till xn. And one more thing has to be clear here is that this message that you see, each of this xi, they come from an input alphabet calligraphic x. Similarly, all the outputs that you see here, yi's, these actually come from the output alphabet y, calligraphic y. Okay. Okay, so the reason that I'm putting here is a capital letter is because this for each x1 there is a corresponding y1 that we'll get, and since this y1 could be any arbitrary thing because of this noise, okay, this can take any value. This should be actually modeled as a random variable, and with each random variable there is a associated distribution to which it associated distribution of the output for each input x1, and so that is characterized by something called channel. And since the output is actually a random variable, I'm denoting it using simply capital letter y1 for the first coordinate. And so, okay, these outputs again, let's complete this communication block. So these outputs are then fed into this block called decoder. Okay, so its job is just the counterpart of this encoding operation. So the note that our original message was coming from this set, right, 1 to m, but the actual channel input was given was something else, it was some n length vector, and therefore in output also you get some n length vector, but the final output that you see at the receiver's end should always come from this one of the messages that you started with, right? So the decoder operation is the decoding operation does that, and it takes essentially input this n length channel output that you get, and then it actually transforms these things uh, to a message called m hat, which is again a random variable. So that's why a capital, which actually belongs to this set, original set that you. Okay, all these blocks you should consider them as some kind of function. Okay, so you give them inputs, and essentially you get it spits out something which is actually the output. Okay, so this is the overall communication block that we have. And quite obvious does it seem here that our goal here should be, as you may guess, the goal here is that the input that you sent, which is little m, it should match or agree with this m hat, the decoded message output, m hat, and it should match most of the number of the times. In terms of mathematics, you say that it should match with this, the m hat should match with m with high probability. Okay, so yeah, that's roughly the goal. So you want to have stated here the input message m matches to hat. That is high. Okay, so that's roughly the point. Okay. So now, yeah, so proceeding further, I will first talk about something called channel. We will mathematically see what do we mean by a channel. When I say something like channel, it has actually somewhat some inputs and then some outputs. How you mathematically define a channel. So as a definition of the channel, so channel is actually, uh, we can think it as a definition. So channel is, we denote the channel as by W, a function, where it takes the input from the calligraphic X and spits out something in this output alphabet, which is Y. Okay. In fact, for each input that you give from this calligraphic X, you have you correspondingly get anything from this, the range of this function, which is Y. Okay, so in some sense, and since the output is actually is an arbitrary output, is a random output, you model the output Y for a particular value of X to be a random variable, and so therefore this channel that you see, which is just nothing but a function, is specified by. So this is point number one, I would say. Second point is that it is specified by conditional distribution, right? Because since Y is an output, it is a random variable and it has to be specified by a distribution. And in particular, since we have conditioned it on the fact that we have always fixed and so therefore to analyze the output, we first basically fixes the input, and that is the conditioning event for us. And so therefore, the output of this channel is specified by a conditional distribution. Okay. In particular, we denote this as a blue of. Okay. So so for example, for an input xt, so the subscript t denotes that in time instant t, let's say your input was xt. Of course, this xt is taking values in calligraphic X. The output that you see, denoted as yt, the tth instant output, is actually a random variable. So I should denote it as using capital letters. So it's actually a random variable which is distributed as this distribution W. Okay. So that's the thing. Now, with this channel, we have a particular assumption for this particular channel. And this assumption will remain throughout this lecture. This assumption is about the memorylessness. Okay. So that essentially means that the tth instant input that you have in this particular example, xt, for example, the tth instant input or sorry, this should be output. So the tth instant output, that is yt here, depends only on the tth instant input, that is input at time t. Okay. And we can actually give a mathematical expression of this memorylessness, that if we say that the channel is memoryless, then what condition it should satisfy. So this is, if you think a little bit, this is pretty simple. So this time, if you consider a joint distribution, so let's say you come back to our communication model. So recall that we are using channel n number of times. We have an input which is an n length sequence, and correspondingly we get an output which is again an n length output. So if you capture the joint distribution of this, right, the two random variables. Okay, so I'm capturing it using w to the power n. So this is actually a product measure or a joint measure, you can say. So this wn, the distribution of this guy, conditioning on the fact that you transmit x1, this joint distribution is actually equal to the product of individual distribution. Okay. And t runs from 1 to. Okay. So this is what implied by the memorylessness of the channel. Okay, this is something we'll assume throughout. Okay. So with that, we'll now review a few channels which are actually very popular in the communication system and in practice as well. So yeah, so I'll talk about few channels that are important in practice. Okay, so we'll begin with the first channel, which is binary symmetric channel. Okay, so binary symmetric channels are specified by a particular parameter, which is delta. In particular, we say that we have a binary symmetric channel VSC, which has got a parameter called delta, or known as the crossover probability. And by that, what we do mean is the following: that for this channel, you have the input alphabet and output alphabet, both are equal, and in fact they are binary field, that is 0 1. So that's why the name binary. And then if for this particular channel, whenever you try to give inputs like 0 and 1, following happens. So for every input 0, and in the output after the channel, if you transmit this 0 to this channel, if you give this input 0 to this channel, the output that you gave, that the output that you receive, it may be anything from 0 or 1. Okay, so with some probability 0 maps to 0, and then with some probability 0 also goes to 1. Similarly, 1 also goes to 0 with some probability, and 1 remains to 1 with some probability. Okay, so now we'll assign probabilities to it. So okay, so that is actually given by this delta. So delta is known as a crossover probability. So the probability with which you cross, you basically invert your bit. Okay, so from 0 you go to 1, and then from 1 to you to go to 0, and so therefore there is a crossover, and the probability of it is actually delta, and the probability with which you don't have an error, or you don't corrupt your symbol or a bit, is actually 1 minus 2. Okay, so of course you can there's no reason to believe that these probabilities are equal. So therefore you can have the case where this the probability of 0 equal to 0. I'll state it here. So the probability of getting 0, conditioning on the fact that you have given an input 1, is actually something like delta 1, and then probability of getting 1 when you give an input 0 is actually delta 2. This may be an abstract way of defining the channel, but then a simple binary channel. But then for the condition when this delta 1 equals to this delta 2, and in fact it is equal to some small delta, let's say some delta, then we say that this channel is a symmetric channel, which is the case here. Okay, so for this case, we have only just one parameter. We don't have delta 1 and delta 2. In fact, we have delta 1 equals to delta 2, which is equal to delta. Okay, so we say that the channel is symmetric. By that, what we essentially mean that no matter on which input value I'm standing, whether I'm standing at 0 or 1, the output distribution that I see is actually same. Okay, the conditional output distribution that I see is actually the same. So if I stand at 0, the way in which I get 0 and 1 is 1 minus delta comma delta, and similarly when I stand at 1, the way I get the messages output, or the output distribution that I get is again 1 minus delta comma delta. So yeah, so the conditional distribution doesn't depend on the input that you actually supply. Okay, so that is the piece here. So delta 1 and delta 2 should not depend on the input messages. It should be same for all the messages. Okay, so that is the case. So that's how we call it as a binary symmetric channel. Okay, now mathematically one can also write this expression, this output that you get on the channel as y equals to x plus, sorry, x XOR z. Okay, so you take XOR operation to any input value x, and this but you take a XOR with some number z, which is actually a random variable and is distributed according to the Bernoulli delta. That means that you generate 1 with probability delta, and you generate 0 with probability 1 minus delta. Okay, so note that for any input x, you actually invert the bit once it gets added to 1, once it gets XORed with 1, and that happens with probability delta. That is, it changes its original message. So 1 changes to 0 or 0 changes to 1 with probability delta. And if it is the input, the input, and it remains same as x, then this z is actually takes the value 0, and that always happens with probability 1 minus delta. So that's from okay, so that was all about binary symmetric channel. Now we'll go to the next one, which is also one of the popular channels in practice, which is known as binary eraser channel. Okay, so this is also specified by the parameter delta. Okay, but unlike the previous case where it was known as the crossover probability, here this delta is known as an eraser probability. Okay, I'll come in a minute why this, what do we mean by this. Yeah, so yes. So again, in order to specify a channel, you need to first specify what is the input that it takes. So the input space that it has is again binary. However, the output space that you have is actually not binary. It actually contains 3 symbols. One is 0, 1, and then eraser symbol. I am denoting using a question mark. So for every input from this set, you get one of these outputs. Okay, so if you try to send 0, then you may get 0 or 1 or question mark, or simply eraser. Okay, this question mark has a special name. This is known as erasers. So your message basically gets erased. You don't know what exactly do you get. Okay. Okay, so this is the model. So you try to send 0, you also try to send 1, and then correspondingly you get 3 outputs. One is 0, one is 1, and then a question mark. Okay, so with probability, now I'll assign a probabilities to each of this. So with probability 1 minus delta, you get your 0 to be 0 at the output. With probability delta, you get a question mark. Similarly, from 1 to 1, you get probability 1 minus delta, and from 1 to question mark, you get it with the probability 1 minus delta. Okay, sorry, this is delta. So this delta here is known as eraser probability of this channel, whereas in the earlier case, this delta was known as the crossover probability of the channel. Okay. Okay. So this is the simple channel. And okay, so at the output, you always know whenever you receive an output, for example, if you receive an output something like 0, then you always know the input, what it actually was, right? If you receive 0, then you always know that the input was 0. And if you receive 1, then you always know that this was 1, because there's no way that you can come from 0 to 1. But if you receive erasers, which is actually the question marks, you never know what was the original message, right? So the only problem here is that whenever your symbol gets erased, you don't know which message it was coming from. Okay. So note that this eraser is actually, it's actually a better channel, I would say, or less noisy channel than the BAC, because whenever you have an error in, let's say, in the binary symmetric channel, you don't know the location of errors. Okay, for example, let's say I am transmitting 010 to a BSC channel. Okay, and then let's say some bits get flipped, and at the end you get 110. But if the same input is given to a BEC channel, it may be true. It is true that let's say the second bit will get erased. That's it. Okay. So now notice that this BSC is a tougher one to get through, right? Because uh, you don't know the location at which bits get flipped, plus you don't know the identity of that particular bit. So there are two things to be solved here. One is the location of the bit where you get an error, and then the identity of the bit. I think, yeah, the location itself is very important to find here. Whereas in BEC, you have a knowledge that, which location you have to decode. Okay. So BEC is actually a bit, easier time to get through compared to BSC. Okay. This is just the heuristic that I'm trying to explain.
It's 8 o'clock.
Okay. So with that, now we'll move to the third very popular channel, practice, which is the additive Gaussian noise. Additive Gaussian noise channel. Again, we need to specify inputs and outputs for this. So for this case, the outputs and input alphabets are actually a continuous uh, real number line. Okay, and since this output is actually a continuous, it takes values in the continuous set. This y is a continuous random variable, and accordingly, the distribution with which the distribution we can associate with this y is actually the PDF. Okay, not the PMF, like in the discrete cases that we had. In particular, we say that for an input x, the y that you will get, it can take different values in R, and for each y, this is the distribution. This is the PDF which is associated with it. Okay. So this sigma square is actually the property of this noise channel. Okay, so this is also, I should write here that this is specified by the mean and the variance. Okay, because this is a continuous distribution. And to understand this better, this green sentence here, you should think that output of this additive Gaussian noise channel to be simply input plus some noise shed. Note that this addition is actually in the real line, in the real field. And this shed is actually a random variable which is distributed as the Gaussian noise with some mean and variance sigma square. For our case here, we are taking its mu to be 0. Okay. Yeah. So of course these two parameters has to be specified when you say that your input is actually getting passed down through additive Gaussian noise channel. So now with that, we'll move on to studying some naive schemes. Simple naive schemes for two channels. One is BEC and another one is BSC. In particular, these schemes that we will discuss here, they are known as repetition codes. Okay. So as a scheme in repetition code, what we essentially do. So whenever we say that we are trying to devise a scheme, then we need to specify what is the encoder that I'm using and what is the decoder that I'm using. Okay. So for this, so we'll consider the different cases one by one. So we'll first talk about the BEC channel, the binary eraser channel. So in repetition code, what the encoder that we have is common for both BEC and BSC. So I'll write it for BEC, let's say. So the encoder is simple. So if you want to, let's say, transmit the input M, okay, the message, which is a single bit message. Suppose you want to simply transmit just 0. Then as an encoder output, you should get X1, X2, and so on in n locations. Okay. So then the output that you get out of this encoder is the following. So X1 is equal to X2, and this is always all the way equal up to xn, and each of the values that you get is actually n. Okay, so you repeat it. Whatever the message that you want to send, you repeat it again and again and again n number of times. So let's say if you want to transmit 0, then you have to have an n length 0 vector, that is an all 0 vector. Or if you want to transmit 1, then you need to repeat this one again and again n number of times. And there are only two messages. So there are only two encoded outputs which is possible to transmit over the channel, which are nothing but just the all 0 or all 1 vector. Okay, and the decoding thing that you will use here, the decoder that we'll use, okay, is the following. So recall that in the BEC channel, yeah. So in the recall that in the BEC channel, the flip there's no chance of getting things flipped, right? Whenever you transmit 0, you will always get 0 with some probability, or it just simply get erased. There's never the case where you actually get things from 0 to 1. Similar cases happens when you try to transmit 1. Okay. So therefore, as a simple decoding rule, we can have the following. So out of this n messages that you transmit along the channel, after the channel which is BEC, the output that you get, let's say it is y1 and so on till yn. Then the decoding rule says that if any of the yi's that you see here is equal to 0, then you say that the input was, the original message was m hat was 0. And similarly, if any of the yi's is equal to 1, then you simply say that m hat was equal to 1. Okay, so this is the decoding rule that we'll follow. Okay, so now for this, when is the possible error? So so now you have specified a decoding error rule, sorry, decoding rule, then there is always an error which is associated with it. It can be correct all the time. So when is the chance of getting error? The only problem here in the BEC that whenever you receive a question mark, you will not be able to say what was the input bit. Okay, so the probability that we're trying to address is the probability of error, which is nothing but the addressing all the events where all the bits, all the n bits gets erased. Then only you will not be able to say, right? Because any one of these n bits you will be able to decode. You can always assign some numbers to it. But the only way you get an error is that when you have erasers at all the n locations, and so therefore the probability of error is actually capturing the probability of this event where all the n bits get erased. Now, of course, by the memoryless property, this is this that this is equal to probability of the first bit getting erased times the probability of second bit getting erased, and so on all the way up to n. And that basically the probability that you get is delta raised to n. Okay. Now, if you want to, make this probability small, for example, let's say we are after, so yeah, we want this error delta n to be small than this probability of error, which is known as epsilon. Let's say so some quantity epsilon. Think epsilon to be a very small number. If you want to decrease this, if you want to design your n in such a way that this probability of error that you get, which is delta raised to n, if you want this condition to be satisfied for every epsilon, then in that case you need to have n at least this much. Okay, so the way to interpret is that for every epsilon, okay, and a channel which is BEC with parameter delta, it said this, BEC with the parameter. So once I specify a channel, the delta is fixed for us. And now epsilon is something which is actually, we can choose. So we choose our favorite epsilon. And then if you want to have a probability of error less than epsilon, then you need to, send the same message with this repetition code or with this encoding scheme n number of times. And then n that actually you should have it depends on both delta and epsilon, and you should have at least these many number of repeated transmissions so as to send just one bit reliably. Okay, by reliably again I mean that you want to receive things most of the time, that is 1 minus epsilon there. Okay, so if the probability of error is actually upper bound, or the probability of error is less than epsilon, we say that at least these many number of channel users are required to transmit a single bit message. So therefore, for this particular channel, the number of bits that you can send per channel use. So one bit message you need to use channel these many number of times. So therefore, by unitary method, you can simply say that in per channel use, you are trying to send 1 by these many number of bits. Okay, so that just simply implies that we can send 1 by the reciprocal of this quantity, which is ln 1 by delta divided by ln 1 by epsilon bits of messages per channel. Okay. Okay, so now we'll move to the second one, the naive scheme for the other channel, which is the BSC delta channel. Okay, again the encoding rule is same, so I can copy that. Because we are relying on the repetition codes. So encoder is the same, but the decoder is different this time. In fact, we'll try to think of an ML decoder, the maximum likelihood decoder. Okay, which is that if you, let's say, get outputs, n length output, and coming out of this alphabet 0, 1, the Cartesian product of this n number of times, then the transition probability you can write, or the conditional distribution you can write of this yn, which is simply yn given x1 to xn, or you simply say e of m, the encoding or the encoded output of m is sent. So you know that the encoded output is always either a all zero vector or a all one vector. So whatever yn that you receive, which is actually a binary vector of length n, you just count the number of times you get the original message m, and you count the number of times you don't get the original message m. Okay, so if message is 0, then you count the number of times you get 0. That means that you essentially will not flip the value of 0 with probability 1 minus delta, and you flip things with probability delta. So the number of times you actually find things equal and you don't flip is actually given by this quantity, which is summation of the indicator random variables of yi equal to m and times delta to the power 1 minus. Okay, so this would be n. Okay, so the total length is n, and out of this length n, there are these many number of symbols which are actually not flipped, which is 1 minus delta to the power this much, and that happens with the probability this much. Again, the things are actually taken. You are taking the product of individual probability. This is again due to the property of memorylessness. So yeah, so the number of times you see a flip is actually n minus the remaining number of times you have the same message. Okay, and that happens with the probability delta. So you take a power of delta. So yeah, the exponent. So that becomes the exponent of this the probability delta. Okay, so the ML decoding rule that we get here is the following. So if you think that the probability of yn, given the chance that m is equal to 0, if you get this probability more than the probability of yn, conditioning m is equals to 1, if you think that this probability is more, this likelihood is more, then the ML decoding rule says that you decode the value to be 0. You take the m hat to be 0, and if you think and if you calculate that this probability is less than this right hand side probability here, then you simply say that your m hat is actually equal to 1. Okay, so that's what the ML decoding rule says. The maximum, these are known as the likelihoods, and the one which the on which conditioning, so the one message or the value of m for which the conditional distribution is maximum, the likelihood is maximum, you say that you decode it to be that bit. Okay, so for if m equals to 0, if this is maximum among these two numbers, then you decode it to be m hat to be 0, and for the other case you decode it to be m hat equals to 1. Okay, so now if you use this the probability distribution here, so okay, so note that I am interchangeably using this W and P, both are the same in the sense. Okay, just that you need to be careful while talking with the Gaussian with the continuous random variable. But this time it is, I think it is okay. So W and P are equivalent. They are just the probability measures. Okay, so now if you try to further solve this, if so when message is 0, the M was 0, the encoded message is all 0 vector. Okay, and therefore you count on the number of times you see ones or and zeros. Okay, so suppose that y1, y2, and so on till yn has k number of ones. Then the question is, how will you decode it? How will you decode this output, and how will you basically find the input and hat from this? Okay. So now simply you see that if you will compute these two numbers, the right hand side probability, likelihood probability, and the left hand side likelihood probability. So when message was 0, the transmitted message was the E of M, the output E of M was equal to all 0. And so therefore the all 0 actually get flipped to 1 at k locations. So therefore the probability in the left hand side that you see here is simply, so you are flipping with probably, so you have k flips. So that happens with delta raised to k, and you don't flip it at all the remaining locations, which are n minus k. Okay, and the decision rules remain the same. So if this is more than other guy, you assign it to be 0. If not, then you assign it to be 0. Now you write the other guy. So if the message is 1, then the encoded message is on all one vector. And so at k number of location, it remains the same, right? Because this is the property of output that we have assumed. And at all the n minus k locations, it actually got flipped from 1 to 0. Okay, so we can, so the probability for that is will be given by the quantity here, which is delta n minus k, because you have things flipped at n minus k locations from 1 to 0, and 1 minus delta simply to the power. Okay, so therefore if you try to solve this, you get something like this. Okay, so now you get this expression. Now there are two cases here. Case one is when delta is less than half. So when delta is less than half, if you think at this, if you stare at this expression here, this is actually, this gets smaller than 1, this fraction delta by 1 minus delta. And therefore, if this is smaller than 1, this base is also smaller than 1. And therefore, the next step that you'll get after this expression here is that we should have 2k. If 2k is greater than n, then the output that you'll get is 1. Okay, and for the other guy it becomes 0. This is again because the base is less than 1. So the if the base is less than 1, then the inequality gets reversed once you, try to cancel out the base and then talk about only exponents. So this is what you get. So that simply implies that if k is greater than n by 2, then you decode it to be 1. If it is not, then you decode it to be 0. Similarly, for the other case, that is the case when delta is greater than half, you get just the inverse of this. So you get the decoding rule that you get. If it is more than n by 2, then you decode it to be 0. If not, then you decode it to be 1. Okay. And rules such like this are known as majority rule. Okay, the more the number of ones that you see, you output, if you see more number of ones, then you output it to be 1. If you see more number of zeros, then you output it to be 0. Okay. So that happens only when delta is less than half. If delta is more than half, that is the chances of getting things, bad, or the crossover property of the chances of getting flipped. If it is more, then you just reverse your decoding. So with that, now we'll again calculate something probability of error. So note that you'll always incur some error if your majority rules fails. Majority rule fails. So that means that if you have more number of errors than n by 2, then you will. So yeah, if you have, let's say, flips at more than n by 2 locations, then you decode it to be 1, but actually the message was 0. This again, this is for the case when the message transmitted is 0, is an all 0 vector. The probability that error that you see actually something like this. So the flips that you get, total number of flips, recall that for BSC we had the following channel model: y was equal to x plus z. I'll introduce a subscript here so as to specify the time instance, and recall that this is just the XOR operation, and this set t was Bernoulli random variables with with success probability delta. So if you see more number of ones, the number of times you see ones, the number of times this input gets flipped. And if this if the input gets flipped by more than n by 2 number of times, then you always commit an error. Okay. So if you see, this probability can again be upper bounded by this event here, just simply 1 by n times t times delta. So this is an upper bound because the set that you are seeing here, the event. So this is actually a superset of this small event. So therefore, the probability of that superset is more than this small event here. Now we can upper bound this guy by this expression here, which is exponential of minus 2 n 1 minus 2 minus delta whole square. Okay, this inequality is already known by the name of Hofstad's inequality. You can simply use this to see that this probability is always less than this. This is exponentially small, and so therefore, if you want this overall probability to be less than the fixed arbitrary probability epsilon, then you must have exponential of 2n minus 1 minus delta whole square has to be less than epsilon, and that essentially implies that your n should be at least this fraction. Okay, so that means that again, in order to get bypass the channel noise, you need to repeat the transmissions n number of times, and where n is at least this much value. Note that this delta is already a fixed quantity which is specified by the channel, which is the BSC channel, and the acceptable probability of error for us is epsilon in this case. And for every epsilon that you choose, the favorite epsilon that you choose, accordingly you need to transmit the same value by using repetition code these many number of times, so as to get the probability of error upper bounded by epsilon. Okay. So therefore, again, if you have these many number of repeated transmissions, you can only transmit just one bit of message reliably, right? And so therefore, we say that we can send just the reciprocal number of these guys. These many number of bits in one channel. Okay. Okay. So yeah, so I have to make a remark here. So I'll write the result that we have got out of this repetition scheme. So for BEC, we get that you can send these many number of bits of messages per channel, which is ln1 by delta. For BEC is ln1 by delta by ln1 by epsilon. Whereas for BSC, you get things these many number of bits per channel. Okay. Now the remark here is that if you want this epsilon to be arbitrarily small, that is for a vanishing epsilon, it is epsilon tends to 0. These transmissions that we see, okay, these number of bits that you see, both of them actually goes to 0. So using repetition code, over BC and BC, we can transmit 0 bits per channel. Okay. So if epsilon tends to 0, then you see that 1 by epsilon goes to infinity, and therefore this fraction goes to 0. So effectively, you are transmitting only 0 bits per channel use if you want a vanishing error probability. So then therefore the question is there a better code or an encoding scheme that can positive number of bits per channel use? Okay. And that brings us to the topic of channel capacity. Okay. Along with the channel capacity, we will also see something very fundamental given by Shannon, which is Shannon's channel coding theorem. Okay. Which actually answers the question that I asked. Okay. So we'll begin with a definition of a channel code. Okay. So is the definition for a channel code. Okay. So before that, I would like you to go back to our example, the communication model example that we had considered earlier. So yeah, so here we wanted to send some messages. Okay, there was a set of M messages, capital M messages, which was encoded to give some N length output, and then so as to make some sense to the channel noise that it sees. And the channel after it is transmitted through the channel, you get the output something like capital Y1, Y2, and so on till Yn. Then we had a decoding operation which again maps the output to this set, which was 1 to m, calling it an m hat. So channel code essentially unifies all the blocks that you see here. Okay, so it talks about the channel noise, it talks about encoding and decoding operation as well. Okay, and all the variables that you see here, n, m, and all those things. Okay, so that's why we need this definition. So a channel code typically specified by two parameters. First is the length, channel code with length n, and size m is simply given by the two mappings. Okay, which are E and D, meaning the encoder and decoder. And we need to specify what is the encoding and the decoding operation. Okay, so this E is actually a mapping from this set to the n Cartesian product of the alphabet set, the input alphabet set. And then the decoder mapping is the mapping of, again, n Cartesian product of the output alphabet to this set back. Okay, to this set again. Okay, 1, 2, and so on till m. Okay, so this specifies the encoder, and then this specifies the decoder. Okay, so with each code, we also have something called the probability of error, which is something like this. So further, we assign or we define the probability of error of this code as the following. Okay, so it is given by this expression. So we are interested in something called probability. So we'll have probability. And so suppose that first message, I mean, in this set of messages 1, 2, 3, and so on till m, let's say this small m is sent. Then conditioning on the fact that m is sent. Okay, so essentially after m is sent after encoding. So you, in the communication block, you essentially send e of m, and then on the reception of noise, you receive it at the so the receiver basically gets y1, y2, and so on as the output, and then amplifies and then sends over the decoder so as to found this output d of yn. Okay, and if the decoded output is not equal to m, it's not equal to m. Okay, then we say that this is a. Okay, and of course this since we have initially chosen a message small m, and this small m can be any one of these capital M number of messages, so we need to take a summation where small m runs from 1 to m, and then we are interested in an average probability of error, so we'll divide it by the overall error. Okay, and we can also simplify this further so as to write this as 1 over m equals to 1 to capital M, and then a summation for yn such that d of yn, you sum over all possible outputs such that the decoded so the decoding of that particular output should not give you m. Okay, or I'll not change the notation. So for the channel notation, we had a w instead of p, is also the conditional probability. So w of n, y of n given e of. Okay, So since we have fixed a channel for the statement, we already have a W. Okay. So a channel code is exists only for a channel W. So in this case, it's a W. And so for this particular channel, we have our transition probability transition matrix, or we can say it's a simply conditional distribution. And if you sum over all possible output, except all those outputs where you get the perfect decoding, that means that T of yn is equals to m, you basically get this particular probability. Okay, fine. Okay, one more point I want to emphasize here, that this equality, the summation that I have bring in for the output is alphabet. This actually assumes that this y space that we are considering, the calligraphic y, is actually a finite set. Okay. Okay. So recall that our earlier goal was to make sure that the things are under control in the communication system. That means that we can control somehow this probability of error, and we basically we want that the decoded output, which was m hat in our earliest example, is equals to the initial message m with the most number of times, that is with large probability. So therefore, we want that this probability has to be small. So essentially, for our control, we want that this probability is actually less than epsilon. I'll use a different color. So here the goal is that this particular error is smaller than epsilon. This is our goal. Okay. Fine. So that's the definition of a channel code. It's just it's just specified by two parameters. One is n, another one is m. M is actually the size, which essentially means the number of messages that you want to actually send out to the channel, and a set of cardinality of set of the messages. So that is essentially size, and then the length with which we are encoding the messages. Okay, that is called as a length, and here it is n. Okay, so now with that we have two facts here, or maybe you can say heuristics. So I'll denote as H1. It says that if so note that there are only three parameters here. Okay, one is m, then there is n, and then there is epsilon. Okay, so there are n number of messages, and the encoding operation allows you to encode things to to a length of n, and we want to make sure that the things are under control, the communication is under control, and for that we essentially want that the probability of error that you see here is actually less than epsilon. Okay, so here is the first heuristic. Yeah. So it says that if, let's say, your m is fixed, that is that you have fixed the number of messages, then what can you say about this n? Okay, so recall that this m was essentially the number of messages, and this n was the output of the encoder. Okay, so I'll quickly go over this again. So yeah, there were m messages, and after encoding, you get n length messages. Okay, out of this m. Okay, so you can think that this n that you see here has to be at least log m, right? Log m based. Okay, because if you don't add any redundancy, so then you will have just the number of bits required to specify one message to be the encoded output length, right, which is n. So and the least value that n can take is simply log m base 2, and the equality holds. I should write here, yeah, and the equality holds when no redundancy is added. Now, if there is no tendency add, then you basically cannot make sure that you have things under control. That basically means that you don't know that the probability of error can be brought down, below this value called epsilon. So there's one more consequence out of this. This means that the decoding error or the probability of error, whichever you like to say, I'm calling it as decoding error. Here, it need not to be in control. Okay, so this is one of the extreme cases where you don't add any redundancy, and you just encode whatever how many the number of bits that you need to express those m number of messages. Okay, so therefore, I mean, and so motivated by the first example, we know that you need to add some redundancy, because there is always a scope of improvement if you add some kind of redundancy. So that based on that heuristic, we basically this H1 basically implies that at this n that you see here, it should be sufficiently large. The amount of redundancy that you add should be sufficient so that there is things are under control, and you brought down the decoding error to be below epsilon. Okay, so therefore you need to add the right amount of redundancy, and therefore that means that the n that you are choosing out of your encoded output, it should be basically this encoding function that you see out of your channel code E. This has to be chosen carefully. This n has to be decided carefully, and it has to be sufficiently large. Okay. For example, if you so for example, it should be something like this, n should be greater than something like n epsilon. Okay. So note that this capital N is epsilon. This is actually just a constant. I should write here the I. Okay. So this is a constant depending on epsilon. So the moment you change your epsilon, the better you guarantee. Let's say you want your epsilon to be very small. So suppose you started with 0.01 and then you want 0.001 to be your epsilon. So therefore you need to control, you want a more control over your communication. So therefore in that case, you need to add more redundancy to your code. And so so n has to be at least this value which are constant, and that constant depends on this epsilon this time. So earlier it was epsilon equals to 0.01, and this time it will be 0.00. Okay, so the constant that you see, it has to cross at least a minimum threshold, which depends on this epsilon. Okay, so that's the first heuristic. Then the second one is also um, very important. It says that suppose now you have fixed your redundancy. Okay, so you recall that we have three quantities here, m, n, and epsilon. So now this time we in H1 we fixed m. Now this time we'll fix n. Then what we can say? Okay. So if n is fixed, that is you have fixed already in the number of output. So length of the output after the encoding operation. If you have fixed that, then what can you say about the number of messages that you can transmit? Okay. So for as of now, I am considering. Okay, so I should write this point again. Yeah. If n is fixed, assuming a finite output space y, the number of messages, or I think the number of, the number of messages that can be transmitted Okay, so as of now, I don't care about the epsilon probability and all. So I'm just asking you a question: is that if n is fixed, that the length, let's say the encoding length is fixed, then assuming that you have a finite output alphabet y, what is the number of messages that you can be transmitted at most? Okay, and if you think carefully a bit, you get the answer to be simply cardinality of pi to the power n. Okay, because you have essentially n blocks to be filled, right? 1, 2, and so on till n. And each of these blocks can take values in cardinality of y number of ways. So therefore, the total number of messages that can be transmitted here is cardinality of y to the power n. Of course, we had not said anything about decoding error probability, whether all these messages will be recovered with high probability or not. Okay, that is something that now we'll talk about this. So now note that if this is the case, that you send out all these messages, then the equality. So this statement, the English statement that you see here essentially means that m has to be less than this thing, and this implies that the equality holds equality holds when m is equals to this guy, and then that is the case when you don't add any amount of redundancy. Okay, and so again, if there is no redundancy added, again things will not be in your control. That means that you can't basically give guarantees to your probability which you actually wanted, right? We initially wanted that this probability has to be less than epsilon. So in order to guarantee this, there has to be a middle way, right? You cannot transmit this many, but there exists something in between. There exists something less than this cardinality of y to the power n. Those messages which you can transfer, right? You can transmit. Okay, so that basically implies that. So I will go step by step. So this basically implies that decoding error again need not be in control, and so therefore, as a conclusion, there should exist a number, call it m and epsilon. I'll talk about why there is a subscript of m and epsilon, which is less than this number, of course, such that so yeah, there always exists a number m and comma epsilon such that the number of messages transmitted using a channel code of length n and decoding error the number of messages m transmitted using a channel code of length n and decoding error at most epsilon satisfies, it always satisfies something like this. M has to be less than m. Okay, So there is a, so you note that in the right hand side, there is a dependence on the subscripts, right? So the subscripts which are n and epsilon, right? So this is because, the better you epsilon you want, you have to modify the, I mean, the lesser the number that you get in the maximum number of messages. Okay. So this is actually mn comma epsilon should be interpreted as something like this. It should be interpreted as the maximum size of a code, or the channel code. Recall that the channel code, the size of a channel code is nothing but just the cardinality of the number of messages that you want to transmit. So this is just the maximum size of channel code, which are of length n, such that decoding error is less than epsilon. Okay, so since this is a maximum size of channel code of length n, with the control that the decoding error is less than epsilon, any messages that any set of messages or any cardinality of number of messages m which does that job has to be less than this maximum value. Okay, so that's the conclusion. Okay. Okay. So now with that, we'll see something very important. This is about the rates, right? So for this particular case, the one that we discussed here in the two H1 and H2. So note that the rate of the messages, sorry, rate of this code, rate of the channel code, which I would like you to recall that this is nothing but just number of the message bits that you transmit, number of message bits you transmit through n number of channel users. Okay. Okay, one form of this we have seen in the first example, very first example, where we essentially use repetition code, and we saw that we are transmitting only just one piece of information, that is one bit of information, but we are using repetition code which uses channel n number of times, and therefore it was simply the reciprocal of n, the value of n that we are getting 1 over. So similar to that, we can also define something called rate of a channel code, and this is nothing but just the number of messages bits divided by the number of channel users used to transmit all the messages. Okay, so for this particular two heuristics that I presented, this can be explicitly written as log 2m as the number of messages base 2, log of number of messages base 2, and it is sent in n number of channels. So this is the rate. Okay, now with the second conclusion that I have, let me call it C2, or yeah, see, this is C2, and this is C1. You see that from C2, since m satisfies this equation, that means that m is less than or equals to m and epsilon, then if I call this rate to be r, then the value of m is simply 2 raised to n r less than or equals to m. Okay, so with this rate, and with this rate such that the rate r satisfies 2 raised to n r less than or equals to m n epsilon. Note that for any epsilon and n, this m n epsilon is always assumed to be given. And so if you have a rate, if you choose a rate r such that 2 raised to n r is less than this quantity, then that basically implies that you can send m number of messages. Okay. So once you have defined r, then the value of m is simply 2 raised to n r. Then you basically, that means that you can send 2 raised to n r number of messages. Okay. Such that the things are under control. That means that decoding error is less than epsilon. Okay. So then the question is very simple. A quick question here is, can we increase this R? Is this the only rate we can use? Note that since rate is simply the ratio of number of message bits that you want to transfer divided by, I mean, and the number of channel users, you always try to maximize this R, right? The more the number of message bits that you can transfer in lesser and lesser number of channel users, you are better, right? So it is more desirable to increase the rate. Okay, I'd like to emphasize on this point. So note that increasing R is always desirable. Okay, but at the same time, we also need to satisfy this thing, right? So that okay, so let me go slow a bit here. So this says that the increasing R is always desirable. So you can always increase this R. I mean, you want to increase this R, but at the same time, you also need to satisfy this constraint, right? So now if I'll increase the left hand side of this, sorry, if I increase the R value in the left hand side, then that basically increases the entire left hand side, right? 2 raised to n R. So that increases. But there, of course, there's a point when this 2 n R actually crosses the left hand side, which is a fixed quantity for us. Okay. So yeah, so there actually exists an R. So that's what I wanted to say again here. So there's one, I'll write it as C3, which is a conclusion 3. It says that there exists an R in between. There exists a R such that, let me call this star, such that LHS is almost equal to RHS. Okay. And we will basically try to characterize this R mathematically. So this is just can be given by the supreme of all the sets. Sorry, so supremum of a set or a sequence of number which is collected, inside this particular set. This is supremum of all the R's in the interval 0, 1, such that 2 raised to n R is less than equals to n1. Okay. This is also can be rewritten or simplified as set of all R's such that R is less than equals to 1 by n log n epsilon based. Okay, so you basically are interested in this particular this particular supremum, which is the supremum of all the rates which satisfy this particular equation, and we call this interesting quantity here to be our C epsilon. Okay, note that this entire thing actually depends on epsilon. Okay, the moment you change your epsilon, then correspondingly you need to also change your n epsilon. That is, that is from the first conclusion that you also need to change your n epsilon, and then you have to choose the length sufficiently large. And if you do that, then then the supreme also, the value of supreme also change, because you can now accommodate like different rates in so as to satisfy this particular condition. And so therefore this is the C that so therefore the entire quantity that you see actually depends on this. Okay, so now to get rid of this epsilon, we'll have a point saying that for a vanishing error probability, to be precise, a decoding error probability, that means that epsilon tends to 0. We have the above supremum that you see is simply limit. You need to consider limits simply limit epsilon tends to 0, CE, that is nothing but limbs of this particular set. Okay. And the quantity that you see, the limiting value that you see of the C epsilon is actually popularly known as the capacity. Okay. This is known as the capacity. Since throughout we have assumed a channel to be fixed, so this is a property of just a channel. Okay. So this is known as the channel capacity. Okay. So this is the quantity known as channel capacity. Now with that, now we have a theorem given by Shannon in 1948 in the seminal paper. It says that for a channel W with input alphabet X, calligraphic X, and output alphabet Y, and it is known that both X and Y are discrete. The CW that you see here, which is defined earlier, is precisely equal to this quantity known as the mutual information. Okay. So this mutual information that you see here can be simply defined as this quantity here, mutual information, can be explicitly defined as this quantity. Okay. So you, since you know the conditional probabilities, you all and assuming some distribution over this input alphabet X, which is Px, you can basically compute this particular information. It's just that you need to find a maximum value of that, and this maximum is taken over all possible distributions you can find over this input alphabet X. Okay. And this max operation here is actually taken. Important point to remember that this max operation is due to the fact that the mutual information that you see, the I of Px and W, the input distribution and the channel W, which is the conditional distribution. It's a concave function. in the distribution Px, the distribution of x over scalar graphic x. So in other words, it just says that the maximum message or you can say that the maximum rate R that you can transmit over a channel W reliably such that this epsilon can be brought down to 0, and provided that your n is sufficiently large with respect to this epsilon, then so that maximum rate is actually given by this particular quantity, which is just the maximum mutual information that you get, and this maximization is over all the input distribution periods. Okay, so that's the Shannon's channel coding, one of the most fundamental results from information theory. We're not going to prove this result. Okay, so that's all I had in this lecture of channel capacity. Thanks for listening.